For millennia, for most of human history, my world was, well, it was incomplete. You see, I am mathematics, and I was a house divided against itself. I spoke in two completely different tongues, and neither one on its own could ever truly capture the universe. On one side, you had geometry. The world of shapes and space, all visual and intuitive, born in the sunshine of ancient Greece. And on the other side, algebra, the world of numbers and symbols, a powerful, precise language perfected during the Islamic Golden Age. Each was brilliant in its own way, but they were separate. They could describe a static, frozen world perfectly, but they just couldn't grasp the one thing that truly defines our reality: change. I mean, just think about a perfect circle. You can see it, right? You can draw it. But how could you possibly capture its flawless, infinite essence using just a handful of symbols? How do you translate something so perfectly visual into a single finite statement? That was the big problem, the wall that kept my two halves apart. Until this one beautiful, elegant line of algebra: x squared plus y squared equals r squared. Now, that's not just some rough sketch or an approximation. It is the circle. Every single point that makes this equation true lies on that circle, and every point on the circle makes the equation true. It's a perfect translation. A bridge between two worlds had finally been built. This idea, this complete game changer, is called coordinate geometry. It was dreamt up in the 1630s by two Frenchmen. One you've probably heard of, the famous philosopher René Descartes, but the other, he was a quiet lawyer named Pierre de Fermat, a man who treated math not as his job but as his passion, a brilliant, brilliant amateur. And this fusion was utterly revolutionary. All of a sudden, humanity had the language to describe a world in constant motion. The arc of a cannonball wasn't just a shape anymore. It was an equation you could solve. The orbit of a planet could be predicted. This new language became the language of physics. For me, well, this was my coming of age. And it was that very same amateur Fermat, having just helped give humanity the tools to master the physical world, who then turned his mind away from the practical to a puzzle of such profound, almost useless beauty. You see, Fermat was just playing around with an old friend of mine, the Pythagorean theorem. You know this one. It's been around for thousands of years, and it's got an infinite number of these neat, tidy, whole number solutions. 3 squared plus 4 squared equals 5 squared. Simple, clean, perfect. But then Fermat asked a question that sounds so simple, you'd think it was a joke. What happens if you just change that little number 2? What if, instead of squaring the numbers, you cube them, or raise them to the 4th power, or the 5th, or any whole number power higher than 2? The result? It's just sheer frustration. Go ahead, try it. 1 cubed plus 2 cubed is 9, which is not a perfect cube. Okay, 2 cubed plus 3 cubed is 35. Nope, not a cube either. No matter what whole numbers you plug in, those clean, elegant solutions just vanish. They're gone. And right here, this is where the real story begins. Around 1637, Fermat was reading an ancient Greek book, and he scribbled a note in the margin right next to this very problem. He wrote that no whole number solutions exist for any power greater than 2. And then he added this legendary, absolutely infuriating sentence. He had a proof, he said, but the margin was too small to write it down. With that one little sentence, Fermat lit a fuse. That note became a legend, an obsession. It was a challenge that would haunt the greatest minds in my world for the next 358 years. And what a quest it turned out to be. This wasn't a one-man job. It was a relay race across centuries. 100 years after Fermat, the great Leonhard Euler finally cracked the case for the power of 3. Others managed to knock down the powers of 5 and 7. In 1847, a mathematician named Gabriel Lemay actually stood up and declared victory, only to have his proof collapse in flames weeks later. The puzzle just would not yield. But here's the crucial part. Every single failure pushed me forward. Lemay's flawed proof, for example, forced another mathematician to invent whole new fields of abstract algebra just to figure out why it failed. The theorem became this graveyard of proofs. But from that rich soil, entirely new branches of my world began to grow. So let's fast forward to the modern hero of this story, Andrew Wiles. He had been obsessed with this problem since he was a kid. And when a new discovery connected Fermat's little puzzle to a deep, modern part of my world, he saw his chance. For 7 years, he worked in total secrecy, locked away, telling almost no one what he was trying to do. Then, in June of 1993 at a conference, he gave a series of talks, finally revealing his proof. He finished with the most understated words imaginable. And I think I'll stop there. The room just exploded. But the story wasn't over. A tiny flaw was found. It took another year of agonizing work, but Wiles, with help from a former student, fixed it. The 358-year quest was, at long last, over. So, why? Why does any of this matter? What was the point of chasing a seemingly useless puzzle for 3.5 centuries? Well, this is where the story gets really beautiful. The prize was never about the destination. Just look at this incredible chain of events. A lawyer scribbles a riddle in a book just for the love of the game. To solve it, generations of the smartest people alive have to invent entirely new ways of understanding numbers, creating this vast, abstract field called number theory. And then, centuries later, that useless field becomes the absolute foundation of modern cryptography, the very thing that keeps our entire digital world secure. The actual answer to Fermat's last theorem, the fact that no solutions exist, it has almost zero practical use. But the tools that were built to find that answer, things like algebraic number theory or strange and beautiful ideas like elliptic curves and modular forms, these are now some of the most powerful concepts in my entire arsenal. The treasure wasn't in the chest, it was the incredible map they had to create just to find it. And that leaves us with one last thought. The story of that little note in a margin is really the story of human curiosity. It's proof of the incredible, unpredictable power of asking questions just for the sake of knowing. So the real question isn't just about the past, it's about right now. What beautiful, seemingly useless puzzle are we chasing today that will unexpectedly build the world of tomorrow?